all the videos are on modules, except for day one. And day one, nothing was working. So, but Thursday's lecture on alkanes is published, and the one on alkenes today will also be published. Okay. And by the way, if you go to Files on Canvas and go to Lab Related, here are the dry labs. Okay. Yes. Okay, so this is the dry lab we're doing today. This is one we're doing next week, and then when we're doing following week. Now there are 3 subunits for unit 1: alkanes, alkenes, and alcohols. And there will be quite a few reactions, particularly with alkenes and alcohols. Yeah. Yes. This needs to be part of your soul. Everyone, eventually you should all print one of these out. Flowchart, and you can use this during the test. I want you to get used to using this flowchart because it talks about the general reactions and conditions. So when you start synthesizing stuff, you're going to find it on here and kind of back up or go forward on here. And it'll really help you. I've been using these for 15 years, same one actually. So they're very helpful. My students find them a really good thing to use. Okay, so anyway, so that if you want to print out your own, or if you miss a lab these next few weeks, you can print it off, go to Canvas, Files, print it off, and they're going to be multiple choice. And what I do is I randomly choose 10 problems, grade those, and that's what your lab score is based upon. Okay, then after that, when we get into wet labs, it's different, really different, but dry labs are all the same. I randomly choose 10 problems, grade those, because there's like 50 problems. It take me forever to grade all those. So what I do is I just choose 10. Okay, any questions about that? Pretty straightforward. Okay, so let's get into the meat of today. Now, one other thing, all these PowerPoint slides are available. I'd recommend you print those off before you come to lecture for that day. That way you can take notes directly on it, like you did. We found in the past, it really helps to do that. Also, you can preview a video. I have the videos from last semester on there as well. And if you go to my YouTube channel, you'll find 10 years worth of videos on this stuff. There's lots and lots of stuff available for you. And the videos can be sometimes a little on the dry side, being nice, but they are what they are. All right. So today we're going to get into alkenes, which are also known as unsaturated hydrocarbons. Remember, hydrocarbons are made up of 3 parts. We have single bonded hydrocarbons, we have double single hydrocarbons, and we have triple double single hydrocarbons. So hydrocarbons is a very generic term. Now, what I'm not going to cover in this class, or at least I'm not going to emphasize it, are triple bonds alkynes, because our body has none of them. And this is an allied health chemistry class. That's why I'm not including triple bonds. Also, I'm not doing commercial polymers. I'm going to be doing biological polymers because it's an allied health class. And that's one less, the alkynes, the triple bonded carbons are one less thing you have to worry about reaction-wise too. Okay. All right, so There's saturated hydrocarbons and unsaturated hydrocarbons. Saturated hydrocarbons only have single carbon-carbon double bonds, no doubles. Unsaturated have either carbon-carbon double bonds or carbon-carbon triple bonds. Also, something called aromatics, and those contain a benzene ring. And the other way to look at a benzene ring, as we'll be getting to that detail here, this is the most common way of writing it, but you may also see it like this. Normally, it's with a circle in the middle of it. 99.9% of the time, I do it with a circle in the middle of it. Now, when you're naming, normally you ignore the mono, di, tri prefix, but you cannot ignore the iso. That's going to be an I in terms of alphabetizing when you're doing naming. Okay, so let's talk about the IUPAC naming. Now, it's the same process every single time we get into a new functional group. What's the longest carbon backbone? Number one. Number two, what's the functional group? Number three, are there any branching? Every single time. Now, in this case, the functional group is going to be a double bond, where last week it was just a hydrogen. Okay, this week is a double bond. We get into alcohols, it's going to be either an OH or a CO. Okay, so let's look at some examples here. Let's name that. Now, right away you go, okay, it's an alkene, it's a carbon double bond. So the functional group is going to be the double bond. So the in fact, let me just, the backbone has to include the functional group, no exceptions. So, for example, that backbone won't work because it doesn't include the double bond. So we have to include this double bond in the backbone. Now, there's two ways to draw that. We can draw it. Oops. Either yellow or green, either one works. Let's use the yellow one. Okay. Now, next thing we have to do is name the carbons, the number of carbons. Okay. There is 1, 2, 3, 4 carbons. And we can name it from left to right, right to left. If we start on the right, the numbers are going to be smaller because the functional group, double bond, that's what we want the lowest number for. So if we number it like 1, 2, 3, 4, because we're using this one, versus 1, 2, 3, 4. So you can see the double bond is in the 1s and 2s is lower than the 3s and 4s. So we're not going to use the green numbering, we're going to use the red numbering. Why? Because the numbers are smaller. Okay, so two things rule in IUPAC naming: small numbers and alphabetizing. So keep those in mind. All right, so we're going to ignore the greens because the reds will give us lower numbers. Okay, now double bonds are kind of weird when you're numbering them. If we start at 1 and go to 2, what carbon hits the double bond first, 1 or 2? It's at first, 1. So that's the carbon number we're going to be using for the location. So this is a 4 carbon. So that's a buta. Double carbons have an ENE functional group name. And where is the carbon where the double bond is located? Carbon number 1. So it's 1-butene. Do we have branching? Oops. We have branching right there. So that's on carbon number 3. So it's 3-methyl-1-butene. Now normally we're going to replace the A with the ene. So really it's and it's only for double bonds. Replacing the A. Normally be a buta, but because it's a double bond, it's going to be a butene. Yeah. Where's the double bond? What carbon number?
Oh, forgot.
Yeah. You got to say what carbon number the functional group is located on. In this case, it starts on carbon number 1. Does that make sense?
Yeah.
Notice my cough. Yeah. Speak up. When would you use it? Well, you have to look at the carbons on the backbone. How many carbons are on that yellow backbone? 4. 4 means buta. If it was 3, it would be propyl. If it was 2, it would be ethyl. 1 methyl. So if you look at the slides from last week, it'll go through those numbering. Okay, so 3-methyl-1-butene. You can also have cycloalkenes. So if it's a cycloalkene, you're going to have to then notate it as such. So let's do a cyclic one. Okay, so let's name that. Right away, you notice it's cyclic. That defines the backbone, the cyclic part. Boom. Okay, and how many are on the backbone? 1, 2, 3, 4, 5, 6. So that's going to be a cyclohexene. And are there any branches? Right here. So how are we going to number this? Okay, well, you can number it 2 ways again. We can start down here. And go clockwise, or we can go here. Now we always number into the double bond, never away from it. So if we were going to start up here, we would go now if we use the blue numbering, that branch is going to have a really high number. So because of that, we're going to use the red numbering. So we're going to say, now in this case, interestingly, if you say 1 cyclohexene, that's fine. If you don't have a number 1 there, it's assumed that it starts at carbon number 1. I like to include it so it's consistent. So you don't have to worry about, well, do I include it this time or is it optional? Why? Just do it. Okay. I'm not going to mark it wrong if you don't have it there or anything like that. So carbon number 3 is where the branch is. So that's 3-methyl. One cyclohexene. Okay, so let's name this guy here. Okay, so we've got double bonds. That means it's going to be an alkene. Let's look at the backbone. Okay, so we're looking at 1, 2, 3, 4, 1, 2, 3, 4. So we have 2 backbones of 4 carbons long that include the double bond. Okay, so this would not count because it doesn't include the double bond. Even though it's longer, would not count. It has to include the functional group. So let's just use this since I've already numbered it. Okay, so we've got 4 carbons long. So it's going to be a butene. And we have a branch on carbon number 2. Okay, so where does the double bond start? On carbon number 1 or carbon number 2? 1. Oops. So that's 1 butene. And then at 2, we have a 1,2-ethyl branch. So it's 2-ethyl, 1-butene. Okay. All right. Now, next week, you can get lots of practice at naming alkenes in dry lab. Also, remember, I have lots of worksheets. If you go to Unit 1, worksheets, lots of worksheets to practice. There's some on alkanes, there's some on alkenes, there's some on alcohols. Lots of practice with answers. Okay, you can also have multiple double bonds. So if we look at this here, okay, that's going to be the backbone, 4 carbons long, but it contains 2 carbon double bonds, 2. That means it's going to be a diene. Okay, so if we number from right to left or left to right, it doesn't really matter. We'll get the same numbering in this case. So it's going to be a butadiene, di meaning 2, and the position is going to be 1, 3. 1,3 butadiene. Okay, and we've got some branching, 2 methyl groups. So we've got 2, 3 dimethyl 1,3 butadiene. Okay. Now, last week we talked about rigidity. Remember, when you get a cyclic alkane, that's rigid. So you need to look for possible cis-trans isomers. Double bonds are also rigid. Look for cis-trans isomers. So when I say rigidity, that means that carbon double bond cannot freely rotate. Carbon-carbon single bonds freely rotate unless they're in a cycle or a cyclic compound. Okay, so if we look at these two butenes, 4 carbons, double bond is on carbon number 2. Those 1,4 methyl groups can either be side by side in a cis configuration or opposed in a trans configuration. And you have to label it likewise, okay? It's just like left and right hand. 5 fingers or 4 fingers and a thumb. Both of them have that. They attach to the palm. Both of them have that, but they're not interchangeable. Not interchangeable. So you have to specify, is this a cis or trans? And that is extremely important in biological compounds because our biological compounds favor one or the other. For example, when we get to carbs, they favor one over the other. They favor the D form. When we get into amino acids, it favors the L form. And you've all heard of trans fats. Trans fats are very bad for you because our natural fats are cis. So it's extremely important that you not consume trans fats. Trans fats are easy to consume if you eat a lot of fried foods. Deep fat fryers tend to make cis bonds convert to trans bonds. So when you pull those wonderful French fries out of the deep fat fryer, you're getting a lot of residual oil, and that residual oil frequently will contain trans bonds, trans fats. Bad. The physical characteristics of cis versus trans are slightly different also. It has to do with intermolecular forces and how they align to one another. Okay, physical properties. Like alkanes, they're very non-polar. They have very low intermolecular forces. That means they have low boiling points, low melting points, and low surface tension. Always are 3 parts. If it has high intermolecular forces, then the boiling point will be unnaturally high, the melting point will be naturally high, and there'll be very strong surface tension. Like water, for example. Water is very, very strong polar tendencies, which is significant biochemically, since most of our body is made up of polar water. Our body is a big pack of water-based reactions. The problem with our body is our body needs to separate those reactions from one another. And it does it using intermolecular forces, something called a biological membrane. Okay, basically, the longer the alkene, the higher the melting point, higher the boiling point. Okay, now, reactions. there are quite a few reactions with alkenes. The thing that's most important to realize that alkenes are not stable compared to alkanes. That's why there are more reactions for alkenes than alkanes, because they want to become more stable by reacting. So we have the natural order of things going from unstable to stable. So if a reaction is taking something that's unstable going to stable, naturally it goes smoothly. If we're going the other way, it doesn't go smoothly at all. It requires usually heat and all kinds of caustic measures. Okay, so in a double bond, I don't know if you learned this in 305, but in a double bond, there are two kinds of electrons, sigma and pi. Sigma electrons are very stable. Pi electrons are very unstable. So the more pi electrons you have, the more unstable it is. Triple bonds have one sigma and two pi's. Double bond has one sigma and one pi. A single bond has only sigma. Okay, so sigma is much more stable than pi. So sigma electrons or sigma bonds, much more stable. And that's the driving force for most of the reactions for alkenes, is this stability difference. Now, we have a double bond, C, double bond C, unstable. Its purpose in life is to become more stable. How does it do that? A number of different ways. One way is to have something to convert the pi bond into a sigma bond. Can do that by adding something across the double bond. And because we're adding it across the double bond, it's called an addition reaction. Four types of addition reactions. We can convert an alkene to an alkane by adding across the double bond hydrogen gas, the catalyst. We can convert it to a halogen by adding a halogen or a halogenic acid across the double bond, like HCl or Cl2. Or we can convert it to an alcohol by adding water across the double bond. And that water is in a acidic environment. Also, one other reaction, spark, combustion. Can always burn them. Okay, so let's take these four reactions, 5 if you count combustion. Okay, so if we were going to add Br2 or say Cl2 across that double bond, it's going to convert that pi bond to a sigma stable bond and then add 2 halogens across that double bond. Now this is what happens. when let's add chlorine. What happens is the sigma bond between the two chlorines adds there, and the pi bond, and again, this is sigma and pi, the pi bond goes up here. So what you end up with is so, for example, if we had um, what would we make? Starting with propene, 3-carbon alkene, we're adding chlorine gas to it. What will we make? This is how they used to make, I should say, pesticides, exactly like this. Back in the 40s and 50s, and in some parts of the world today, they use chlorinated hydrocarbons for pesticides because insects hate them. They're very effective against insects. Unfortunately, they're also effective in birds. Oh,
Get home without it because my coffee is here. I got it.
okay. So again, this is how they used to make chlorinated hydrocarbons pesticides. In fact, my wife used to work at Davis in a toxicology lab, and one of the current products is called toxaphene. Toxaphene is, by its name, is really a badass pesticide. It kills everything. They can only use it on cotton because cotton is not consumed. It's consumed by cattle, however. And what it does is they spray with hydrocarbons this chlorinated mixture. You end up with all these different compounds, thousands of them. And that's why it's so effective, is because insects can't build up a resistance because there are thousands of them. And unfortunately for us, it's the same problem. It gets into our system. So they don't use that anymore. But back in the 70s, they were using it down by Bakersfield. They grow a lot of cotton down there, and they used to use it widespread down there. Okay, so these are the conditions. We start with our reactants. In this case, it's called 1-propene. Conditions are Cl2. And what are we going to make? Well, that Cl2 is going to add across that double bond. So we're going to end up with now we have to name it. So naming it is going to be 1,2-dichloropropane. So reactants, products, conditions. Every single reaction. Name the reactants, name the conditions, name the products for full credit on a reaction problem. Okay, so does this reaction make sense? This is the simplest of the alkene reactions. It's addition of a homogeneous either Cl2 or Br2. Okay, let's do another example. Okay, so let's add the Cl2 across that double bond. So first thing we need to do is name our reactants. So this is going to be a 1, 2, 3, 4, 4-carbon backbone. So it's going to be a butene. 1, 2, 3, 4. Okay, so we can go left to right, right to left numbering. Which numbering would be best? Blue or red? Why blue? That's correct. Why? Who said blue? No one's willing to. The numbers are smaller. The numbers for that branch next to the double bond is going to be smaller. So we're going to use the blue numbering this time. So, okay, so it's going to be a 2-butene. Because the double bond starts on carbon number 2. A branch is at also carbon number 2, so that's 2-methyl 2-butene. Okay, is everyone okay with that name now? Okay, now the chlorine is going to add 1 chlorine across that double bond on either side. So it's going to be so we're going to name it the same as we did originally. So now it's going to be a butane because it doesn't have any more double bonds. So it's going to be, we have 2 branches now, 2 chlorines. So it's going to be 2,3 dichloro. Is the methyl going to come before the chloro or after the chloro? Remember, alphabetize. After, right. So it's going to be 2. So 2,3-dichloro 2-methyl butane. Okay. Reactants, products, conditions. Yeah.
So when there are no double bonds, we're using the functional group A and E. And then when there are double bonds, we're gonna use E and E.
Exactly.
Okay.
Exactly. So what we did is you converted the double to a single. That's why I went to an ene to an ane. All right, are we all okay with this? Okay, so let's go on now. Instead of adding Cl2 across the double bond, what if we added HCl across the double bond? Just one more simple one here. Let's add, instead of Cl2, let's add H2. Because it's more consistent with the Cl2. So if we're looking at PT is platinum, you have to have a catalyst whenever we add hydrogen. So a number of metal catalysts work. Frequently, they use PT. You can also just say metal catalyst. Either way, it's fine. Okay, So the H now is just going to add across that double bond. So what we end up with is that. So we go from an alkene to an alkane. Who's heard of Crisco? Okay, this is how they used to make Crisco. They used to take corn oil, which has got double bonds in it, and they used to hydrogenate it. When they hydrogenated it, it changed intermolecular forces. It made it more like an alkane than an alkene. Alkanes are much more dense. They're more like lard. So in the 50s, everyone uses Crisco. They didn't want to use lard because they thought it was not as healthy. So I was raised on Crisco. My mom made her own pies all the time and always used Crisco. Well, sometimes the hydrogenation process isn't complete. So you get a partial hydrogenation. And guess what it makes? It makes a partial hydrogenation, trans fats. So Crisco is loaded with trans fats. Now, when they started labeling trans fats on foods, Crisco almost went out of business. They had to figure out a new way to make Crisco without hydrogenation. And they do it now through a mixture of different oils and stuff, which is Crisco is fine to use, no trans fat in it. But the old Crisco was horrible. That's probably why I have such bad asthma, trans fats. So anyway, hydrogenation, fancy word for adding H's across the double bond. So if we want to hydrogenate a double bond, we add hydrogen gas plus a metal catalyst like platinum. So it's very similar to adding Cl2 or Br2. Very, very similar. Only you don't end up with a chlorinated hydrocarbon, you end up with an alkane. Okay, now we are going to talk about something called Markovnikov's rule. Now, remember, whenever we have a mixture, I always said you have to circle the one that's most stable. And there are two arguments as one being more stable than the other. One is symmetry. The other is Markovnikov's rule. Basically, Markovnikov says the more hydrogens terminally, the more stable it is. More hydrogens terminally, the more stable it is. So sometimes when you're looking at two compounds, the number of terminal hydrogens are equal. So that means Markovnikov rule doesn't come into play, but there's usually a symmetry rule you can apply. In other words, when I say symmetry, is it look balanced? Is it balanced? So if we add some two butenes, we have one butene, two butene. And if you got that as a mixture in a reaction, you'd have to circle the one that's the most stable. So test number one, which is more symmetrical, top or bottom? Bottom. So symmetry wins out. Number two, so what I usually do is Okay. So then we have symmetry and Markovnikov. Okay, the top one is unsymmetrical. So that's no. Bottom one is yes. Okay, what about Markovnikov? Okay, how many hydrogens are on the left side of the top one? Because you got carbons here, so there's hydrogens here. That's a carbon. We have 2. What about on the other side? How many hydrogens? 3. Okay, so that means Markovnikov says 5 carbons. Okay, what about the bottom one? 3 and 3. So the bottom one wins out 2 ways: more symmetrical, and Markovnikov's rule, it's got more terminal hydrogens present. So that's the one you'd be circling. So whenever you have a mix, always circle the one that you feel is the most stable. And that's going to be like a 60-40 mixture, because life is not black and white. As you already know, all of you have lived enough life to know that life is not black and white. It's always gray. So whenever you have a reaction, you always have a mixture. So we have symmetry and Markovnikov. Okay, so let's now add an acid across a double bond, like hydrochloric acid, HCl. Okay, so let's take so what is this thing here? It's a 1, 2, 3, 4, 5. So it's a pentene and so the 2-pentene. Okay, so reactants, name it. Conditions, hydrochloric acid, HCl. This could be HBr also, or HI. Most of the time it's going to be HCl. So what's going to happen now is we're going to get a mixture. So whenever we are adding HCl, most of the time we're going to have a mixture. Because before we didn't have a mixture because of ClCl. Now we have HCl. So we're not going to add proportionally. So situation number 1. That HCl is going to add where we have so the HCl is going to add directly across the double bond with the H on the left, Cl on the right. Statistically, though, half the time it's going to be HCl. The other half the time is going to be ClH. If it's ClH, we're not going to have that, where it's going to look like that. Okay, it's purely statistics. Half the time it's going to be HCl, other half is going to be ClH. And when that happens, you have a mixture. So now we have to figure out, which is more stable? Well, which is more stable? Okay, we've got Markovnikov symmetry. Does everyone see how I got these two products? It's just how it aligns across the double bond. Okay, so Markovnikov, we've got 3 H's, three H's, 3 H's, 3 H's. So Markovnikov really doesn't tell us much because there's 3 and 3. Okay. What about symmetry? Which is more stable, top or bottom? And again, symmetry is going to be, is it balanced? Top or bottom? Well, look at the bottom one now. We've got 1, 2, 3, 4, 5. So it's a pentane. Carbon number 3, we've got a Cl group, which is kind of balanced on either side. At the top, the chlorine is off to the right. So the bottom one is going to be more symmetrical than the top one. Okay, does that make sense? It's balanced. So if you take this one and flip it, it'll look the same. So it's symmetrical. The top one, if you flip it, and the chlorine is going to be on the left rather than on the right. Does that make sense? So between the two, we are going to circle the bottom one. So symmetry loses out on the top. Symmetry wins in the bottom. Markovnikov is a push on both of them. Now we need to, okay, we've named the reactants. We've named the conditions, HCl. Now we need to name the products. 2 names now. We name the bottom one, it's a 5-carbon backbone. Carbon number 3 is the chlorine, so it's going to be 3 chloro pentane. Top one's going to be 2 chloro pentane. So having all those parts gives you full credit on this problem. Now, most of the time, when we're looking, there's some exceptions, and we get into alcohols and ethers, there's an exception there. Most of the time, though, you're looking at the back remains the same. So this is a 5-carbon backbone. It's going to make 5-carbon backbone products. If you're trying to figure out how to make this, the 5-carbon backbone, so you're going to have a 5-carbon backbone as a reactant. And then I'll show you the exception when we get to our alcohol ether chapter. Okay, we okay on figuring out which is more stable in this? Now, something similar to HCl is if we add water across the double bond. As water, I want you to think of water not as H2O, but as H-OH. H-OH. So really, we're adding a hydrogen and we're adding an OH. across the double bond. And for the same reason that HCl statistically has got an H on the left, sometimes an H on the right, water is the same way. Got an H on the left, sometimes the H is on the right. So we're going to end up with a mixture with whenever we add water. And again, it's under acidic conditions. Sometimes you'll see it like this. Sometimes you'll usually use H2SO4. We use sulfuric acid a lot in organic chemistry, a lot. Okay. So when we add water, we're making an alcohol. An alcohol has an OH group. So we're starting to get into the reactions of our subunit number 3 by adding water. So let's do an example adding water. Okay, so the conditions are we have reactants, conditions are water and acid, products are an alcohol. So let's add water and sulfuric acid to 1, 2, 3, 4. This would be 2-butene. No branches. So we're going to get a mix. So whenever you add HCl or water across a double bond, expect a mix. And if you look on your printout, it should say mix. It says expect mix. Okay, so that means the HCl, excuse me, the water, is first going to add like that. And it's going to add the other way. In fact, let's change this to pentene. There's a reason for that is okay. So water, just like HCl, will add across the double bond 2 different ways. 2 different ways. Okay, so we have a mixture which is more stable. Okay, let's see now here. We have okay, so let's name our products. Well, top one's going to be which numbering, blue or red? What? Red. So that's going to be it's 5. Alcohols, functional group name is OL. So this is going to be a pentanol, and it's at position 2. So 2-pentanol. Using this is going to be 3-pentanol. Okay, so we have a mixture. Which is more stable? Okay, we do the same kind of arguments again. We have Markovnikov, symmetry, Markovnikov, symmetry. Okay, so symmetry on the top is not symmetrical. Symmetry in the bottom is the OH is exactly in the middle. So symmetry in the bottom is yes. We have 3 hydrogens, 3 hydrogens, 3 hydrogens, 3 hydrogens. So Markovnikov is the same on both. So the symmetry tells us the bottom one is more stable because it's symmetrical. Symmetrical about carbon number 3. That's where the OH is. So those are the 4 types of addition reactions. We have H2, Cl2, HCl, and HOH, or water. 4 addition reactions across the double bond. Why does it work? I'm going to ask you this question. If in doubt, always say, what should you always say? Why something works or not? What runs the universe? More stable. Stability rules. It's more stable. And remember that. And if in doubt, what's the driving force? You know, when you get into some sophisticated chemistry, they say, oh, that's a Gibbs free energy argument, blah, 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 blah. It's stability. Stability. Okay. Now, there are 2 kinds of compounds in general, aliphatic and aromatic. As soon as you see the word aromatic, benzene, or a fused benzene ring. Now, when it says structural relatives, it's talking about, for example, we could have so as long as there's at least one benzene ring in there, 6-membered, every other single, double, single, double bonds, it's aromatic. Now, the thing about benzene, it is super stable. And for a long time, they thought it didn't react with anything. Well, they still think that, but it has its own little issues. One is because it doesn't react with anything, it can easily insert itself where it shouldn't be. For example, in a duplicating DNA structure, where you've got transcription going on, and it'll get in between the helix structure and mess up the transcription process. So in general, benzene products don't react because they're so stable. Now, the problem with benzene products is naming is a pain because it depends whether it's a base product or a branch, and they're named differently. Same compound, named differently, unfortunately. Okay, if benzene is the base, you're going to see benzene in the name. So this is an ethyl group, so it's ethylbenzene. Nitro group, nitrobenzene, bromobenzene, chlorobenzene. Because benzene is the base. That's the only time you'll see the word benzene used in the name. Now, there's also benzoic acid and some other aniline, which is an amino group on, but it's basically benzene. And sometimes these have common names. For example, that's called toluene or methylbenzene, common name. Toluene is used a lot in organic chemistry as a replacement for benzene. Okay, there's an alcohol-based benzene, phenol. A lot of you have heard that. It has some unique properties, phenol. If it has an amino group, it's called aniline. If it has an acidic group, it's called benzoic acid. Now it says IUPAC accepted. That means that these are used so commonly, like IUPAC accepts water instead of dihydrogen monoxide, but it's not the correct IUPAC name. It's IUPAC accepted. Okay, now this is the tricky part. If the benzene is a branch, it doesn't have the word benzene in it. It has the word phenyl in it. So for example, here, we've got 1, 2, 3, 4, 5, 6, 7 carbons in the backbone. And on carbon number 4 is the benzene branch, but we name it 4-phenyl-heptane. And this confuses students all the time. Is it the base or is it a branch? Branch phenyl, base benzene. Now, when you see it written, you will not see it written like this. You'll see it written like that. Rarely you'll see C65. Rarely. So get used to writing it like this here. So to name this would be, okay, it's a 4-membered cyclobutane. And it's got 2 branches on carbon number 1. So it's 1,1-diphenyl cyclobutane. Now, this is kind of an old world naming. So if you have 2 branches on a benzene ring, there are 2 ways to name it. Old world, new world. New world uses numbers, old world uses these esoteric words like ortho, meta, para. Ortho means the two branches are together. Think of the word or, little bitty word, close together. Meta, think of meta meaning in the middle. And then para, think of paragliding. Paragliders got wings spread out directly across from one another. So when the branches are directly across from one another, it's called para. Now, that's one way of naming these. The other way to name them would be 1,2-dibromobenzene versus ortho-dibromobenzene. 1,3-dibromobenzene, meta-dibromobenzene. And lastly, para-dibromobenzene, 1,4. Both of those are acceptable. And you'll see the ortho, meta, para used a lot in nutritional periodicals, a little bit on older biological journals, but they're getting away from that just because it's not as descriptive. Now, the groups don't have to be the same if there are two. You can still use the ortho, meta, para. But if there's more than three, you can't use that. Okay. Aromatic compounds are very similar to alkanes and alkenes, very low IMF. So low boiling point, low melting point, low surface tension. Okay, now aromatic rings, not relatively stable, stable. Very, very stable. Now, when you burn a fire, you're camping out and you're burning a fire and you want to cook some eggs in a frying pan. You put the frying pan over your fire. What's the bottom of the frying pan look like after you're done? Is it still shiny? Very black. That's because it's unburned carbon is sticking to the bottom of the pan because there's insufficient amount of oxygen. That dark stuff is really bad for you because it's mostly made up of benzene-like chemicals. Think of another situation. Take your chicken and you marinate it. A little teriyaki sauce, a little bit of sugar, ginger, garlic, and you put it on your barbecue and the barbecue is too hot. What happens to your chicken? What color does your chicken turn? None of you have done this? Huh? It burns, right. And what color is the burned? Black. So you have two colors on your chicken, brown and black. If it's black, it's bad. If it's brown, it's good. Now, brown means it's something called a browning reaction, and that's where all the flavor is. As soon as it goes to black, that means it's a benzene-based product. Not good. That's why they say eating barbecue every day is very unhealthy. It's because of the blackness on the barbecue. Chimney sweeps in the Middle East, not in the Middle East, in the Midwest. We're getting bladder cancer more than the rest of the chimney sweeps around the country. And they found out that the chimney sweeps were getting this chemical from your fireplace that sticks to the inside of your fireplace chimney. And of course, to get all that junk out, called creosote, they would take a big brush and go, and they'd be breathing that in. They ended up with bladder cancer at a higher rate than the rest of the country. And they found out that black stuff is related to benzene, called polyphenolics. So, and again, it's the same old thing. It's these real stable benzene products that mess up your DNA. Now, I don't want you to worry about Okay, so you're responsible for unit 1, the benzene with an alcohol, phenol. Also toluene. Those are 2 common names. The rest of these we'll come to as we come to them in the subsequent chapters. Okay. Our body has a ton of benzene-like structures. A ton. I mean, a ton. Extremely common. And your body works with it fine. Vitamins, it just goes on and on and on and on. And these will be the related structures. And these are all badass. These are not nice chemicals. This is what caused the bladder cancer in the chimney sweeps in the Midwest. These guys here. And this is also when you overcook your barbecue and you get that black stuff on there. This is what's present. I think we're done. Okay, so as you notice, this unit has got a lot more reactions than in our subunit 1. Now in lab today, what time is it? I'm going to get out early today. Dry lab 1 is on alkenes. And it's a worksheet. You can work in groups if you like. And I would like you to finish it in lab because I'll be there to answer questions and stuff. You may work in groups or by yourself, whatever you feel most comfortable. And you're going to be scanning that and uploading it to assignment Dry Lab 1. Also, don't forget about your the safety contract and the waiver. Easy points. Yeah. Yeah. So if you want to do it electronically, for example, today, you have lab today? Okay. So you can either take it from me or you can download it and do it electronically. So if you go to Canvas, Files, Lab Related, you should see Dry Lab 1, 2, and 3. And that's fine. You want to do it electronically. A lot of you feel much more comfortable doing it electronically. I'm kind of a old school. I was born in 1950. So for me, electronics has entered my life later in life. Okay. That's what I had for you for today. Okay. So are there any questions about this chapter? This chapter has a lot more reactions. When we get to the next chapter on alcohols and ethers, there's a lot more reactions as well. So you're going to end up with like 12 or so reactions. In fact, okay, at the end of unit 1, you're going to have 11 or 12 reactions counting combustion. That means reactions going forward, going backwards, reactants, products, conditions. Now, Thursday, we're going to talk about alcohols, but I want to go over lots of problems, synthesis problems on Thursday, and just talk through them. Okay. All right. So that's what I had for you today. I will see Tuesday folks upstairs at 3, or you can go up there earlier. Are there any questions about anything?